Well, students, we are discussing methods for approximating an isolated root of a single nonlinear equation. In this, we have completed closed domain methods, and in this class, we will start our discussion on open domain methods. In that, let us take secant method as the first topic to discuss. Secant method is not something new to us. It is exactly the same as the regular falsy method. Only thing is that we don't need to locate a root of our equation, which is the first and foremost step of the regular falsy method. Recall, in the regular falsy method, we first have to locate the root or of the equation f of x equal to 0 in an interval, say a0 to b0, and then we will draw the line joining the points a0 f of a0 and b0 f of b0, and see the point of intersection of this line with the x-axis. We call this point of intersection as x1, and that is the first term of our sequence. Once we have this, we will go ahead to see on which part of this interval does the root lie, and we accept that part of the interval and discard the other part. And our iteration goes like this. Now the question is, why should we take the initial guesses a0 and b0 on either side of the root R? What happens if we choose both these numbers on one side of the root? For instance, let us take b0 also to be on the left side of R, say something like this, and look for the line joining the points a0 f of a0 and b0 f of b0, like what we used to do in the regular falsy method, but now b0 is not chosen in such a way that our interval a0 to b0 contains at least one root. Now what happens if we look for this line, that is the line joining these 2 points? We can see that that line may also go and intersect the x-axis, and you take this as now your x1, or let us change the notation little bit and call this as x0, this as x1 and this as x2. Now what you do, you discard this point, take x1 comma f of x1, that is this point, and x2 f of x2, and again look for the line joining these 2 points now. And take the point of intersection of this line with the x-axis and call this as x3. For x4, you discard x1, take x2 and x3 and generate x4 and keep going like this. In this particular example, this also seems to be working. That is, it generates a sequence, and that seems to be going closer and closer to your root R, right? That is the main idea of the secant method. Let me again repeat. The secant method is a straightforward modification of the regular falsy method. The only difference is that we do not demand the initial guesses a0, b0 to be on the either side of a root. That is the only difference in the secant method. But otherwise, the underlying idea, the main core method remains the same. But one big problem with secant method is that it may happen that at some stage you may get f of xn is equal to f of xn minus 1. Say for instance, if you have your function graph like this, and it may happen that your xn and xn minus 1 may be in such a way that f of xn is equal to f of xn minus 1. In that case, what happens? Since we are looking for the line joining these 2 points with the x-axis, and in this case, the line is parallel to the x-axis, it will never intersect the x-axis. This is the geometrical explanation for why secant method can fail. It may happen with the initial guess also, but since initial guess is in our hand, we may carefully choose our initial guess in such a way that this condition does not hold at the initial level. That is, we may always choose our x0 and x1 such that f of x0 is not equal to f of x1. But however, we cannot give guarantee that such a situation will never occur at the later stage. It might occur at a later stage, but carefully observe that this situation will never occur in the regular falsy method. That's the main disadvantage of secant method. But a very good advantage is that you can simply choose x0 and x1 as you like. We don't need to search for these two numbers in such a way that there is at least one root between them. So that makes secant method more flexible to implement on a computer, unlike regular falsy method. Let us formally define the secant method. You give me any x0 and x1, of course, in such a way that f of x0 is not equal to f of x1. Then from here, I can generate x2. Then you take x1 and x2 and generate x3, and take x2 and x3, generate x4, and you keep on going like this. How will you generate all these numbers? Well, you will use this formula or equivalently this formula to generate these numbers. This idea is exactly the same as what we did with the regular falsy method. In regular falsy method, in fact, we have seen why such a formula is coming to us. It is very apparent from the geometrical interpretation. And also we discussed the stopping criteria for regular falsy method when we go to implement the method on a computer. The same stopping criteria idea will also go on with secant method. Not only secant method, the same stopping criteria idea will go through with other method that we are going to discuss also. Therefore, I will not discuss the stopping criteria again. It is exactly the same as what we did in the last class for secant method, for Newton-Raphson method, and also for the fixed point iteration method. Stopping criteria remains the same. In the secant method, the sequences xn is generated in such a way that the number xn is obtained by looking at the line joining these 2 points with the x-axis. If you recall from your elementary geometry, this line is generally called secant line, and that is why we have the name secant method. As I told, it is evident that secant method can fail if at any iteration you come across such a situation, that is f of xn minus 1 is equal to f of xn. As I told you, you should think why such a situation will never occur for regular falsy method. Now the question is, suppose such a situation is not occurring and you don't stop your iteration at any term xn, then you will keep on going with this calculation and you will land up with a sequence of real numbers generated by the secant method iteration formula. And now the question is, does this sequence converge? Then the next question is, if so, is the limit a root of the equation f of x equal to 0? So these are the questions we have to answer. Let us answer these two questions through this theorem. Here we have two hypotheses for the convergence of secant method. The first one is, we want our function f to be C2, that is twice continuously differentiable, and the root that we are interested in is a simple root, means f dash of r is not equal to 0. If you ensure these two conditions and you are interested in capturing the root r using secant method, well, you have to choose your x0 and x1 sufficiently close to the root. This is equivalent to saying that if there exists a delta greater than 0 such that your choice x0 and x1 lies in the delta neighborhood, then you have these conclusions. What are they? The secant method gives us a well-defined sequence of real numbers. It means you will never encounter a situation where f of xn is equal to f of xn minus 1. So that will make sure that your sequence is well defined. And the next one is that all the members of this sequence will also lie in the delta neighborhood from where you chose your x0 and x1. And the third conclusion, which is more important for us, is that that sequence will converge, and the limit of the sequence is R, which we are interested in. And not only that, the theorem also gives you the order of convergence of secant method, and the order of convergence is 1.62. How we conclude this? We conclude this from this expression. I will explain this expression and also connect it with the definition that we gave in the first chapter of our course regarding what is meant by order of convergence. Let us now try to prove this theorem. Let us first derive this expression. Well, this expression is not going to directly prove any of our conclusion, but it is the main expression used in proving all the conclusions that we have listed in our theorem. And this expression has to be proved for all n is equal to 2, 3, and so on, whenever xn minus 1 is not equal to xn is not equal to r. Remember, there are two parameters, xi n and zeta n. We have to prove their existence in this expression. Let us see how to derive this expression. From the secant method formula, you can see that x equal to xn plus 1 is a root of the equation g of x equal to 0, where g of x is given by this expression. This is not very difficult to show because if you recall, the secant method formula is given by xn plus 1 is equal to xn minus f of xn into xn minus 1 divided by f of xn minus f of xn minus 1, right? From here, we can do a simple manipulation to get the expression xn plus 1 minus xn into f of xn minus f of xn minus 1 divided by xn minus 1, and then plus f of xn is equal to 0, because we have taken all the terms on the right hand side to left hand side. And now you see, I'm just replacing this by x. That is how I got the definition of g. And therefore, when I substitute x equal to xn, you will clearly get the right hand side expression here equal to 0. Therefore, g of xn plus 1 is actually equal to 0. In other words, x equal to xn plus 1 is a root of the equation g of x equal to 0. Now, using g, we will define a new function psi of t is equal to f of t. Remember, f is the function with which we have considered our equation f of x equal to 0. This is how the function f is coming into our picture, and that f minus the g that we have just now defined minus this expression times t minus xn into t minus xn minus 1. So that is the way our function psi is defined, where x is some number fixed in such a way that x is not equal to xn as well as xn minus 1. Otherwise, this denominator will create problem, right? Here, t is a variable and x is just a fixed parameter. Once you have this function psi, we can make some important observations of this function. The first one is psi is a C2 function. Why? Because f is a C2 function, that is what we have assumed. G is also a C2 function because basically G is a polynomial of degree 1, right? Therefore, it's a C2 function. Therefore, you can see that psi is a C2 function, and also you can see that psi vanishes at t equal to x, t equal to xn minus 1, and t is equal to xn as well. Therefore, roughly you can see that psi graphically something like this, right? You can find a xi1 and xi2 such that psi dash vanishes at xi1 and xi2. How can you conclude that? Well, using Rolle's theorem, we can conclude this. So, as far as psi dash is concerned, you have the graph of psi dash is something like this. And therefore, you can find a number, say zeta, such that psi double dash vanishes. That is, psi double dash of eta is equal to 0. Again, how can you conclude it? Using Rolle's theorem, you can see that there exists a psi, well, let us denote it by zeta n, such that psi double dash of zeta n equal to 0. Surely, zeta n lies between xn minus 1, xn and x, because psi 1 and psi 2 are lying between these three numbers, and therefore zeta n will also lie between these three numbers. But what is psi double dash of t? It is nothing but f double dash of t minus g double dash of t minus this expression. Remember, we are differentiating psi with respect to t, and this is a quadratic polynomial. It's a monic polynomial. Therefore, the second derivative of it is 2. In this, you can see that g double dash is 0 because g is a polynomial of degree 1. And now you put t is equal to zeta n. You can see that f of x minus g of x is equal to 1 by 2 times x minus xn minus 1 into x minus xn times f double dash of zeta n, right? Because this is 0, so you can bring this and this to the other side and write this expression. Therefore, we get this. This holds for any x not equal to xn minus 1 as well as x not equal to xn. Remember, we have already assumed that xn is not equal to xn minus 1. In particular, we always also take r not equal to xn and xn minus 1. Therefore, in particular, we can take x equal to r also, and the same expression will hold for x equal to r, right? So when you take x equal to r in our derived expression, you can see that the first term goes to 0 because f of r equal to 0. That is what we have assumed in our theorem, that r is a simple root. In particular, it is a root. Therefore, f of r equal to 0. And therefore, we will be left out with this expression for g of r. Now, we have already defined g in such a way that g of x n plus 1 equal to 0. Therefore, I can simply add g of x n plus 1 to this expression. It will not disturb anything in the expression, right? It is as it is. Now you see, since r is not equal to xn plus 1 as well, because we always assume that we have generated a sequence. It means we have never touched the root r at any finite n. That is how we have landed up with a sequence. Therefore, throughout this theorem, we can assume that xn is not equal to r for all n without loss of generality. Now you can apply mean value theorem here. What you will get, this will be equal to sum g dash of say zeta times xn plus 1 minus r, right? So that I can substitute on the left hand side to get this entire term is equal to xn plus 1 minus r into g dash of sum xi, which is equal to the right hand side is kept as it is. Now you see, we are almost nearing to the expression that we want to prove. If you recall, what we want to prove is this expression. We got everything, but here we have a g dash. You can see here. Otherwise, everything is achieved. Now, how to handle this g dash? Let us see. We have so far achieved this expression. And let us see how g dash is defined. We know what is g. You just differentiate g to get this expression. And again, since xn and xn minus 1 are distinct numbers, you can apply mean value theorem to this term. And that will give us xn minus 1 times f dash of some zeta, which we will call as zeta n, right? So you can substitute here and cancel this xn minus 1 term and thereby get g dash of xi is equal to f dash of xi n for some xi n lying between xn minus 1 and xn. Now you see, we got exactly what we want. You just substitute this into this expression to get what we actually want to show. This expression is the key for proving all the conclusions that we have listed in the theorem. Let us see how to use this expression to prove the convergence first.